I'll be taking you through the solar system that we have here for training simulation. Here we have our light that we can adjust to simulate the sun. Okay, in Jamaica we have an angle of 20% towards the sun, and this angle will then give us the maximum power that we can get at a fixed rate. However, throughout the day, the sun, as we know, goes from one to the other, right? So with solar tracking systems, we are able to then change the angle of the solar panel. That way we can get maximum voltage outputs. We are able to change that to simulate the time of year that we have around each location. So here we can see that we have a voltage of 19.77 volts. Now this voltage is a DC voltage, direct current. This is not the typical voltage that you'll have in your outlets at home. This voltage you can relate to your car battery, okay? This direct voltage is then converted to AC voltage, which is in your house, so that it can be used by our loads. Here, this system shows all our different transformers, circuit breakers, and our module arrays. This is our solar plant, our simulated solar plant, which gives a maximum output of 500 volts DC. So now I'll be simulating the brightness of the sun, and that can be changed via cloud coverage. So now we can see that we're getting an output of 19.74 volts DC and a current of 0 amps, and this is because we're doing an open current test. So during the short circuit test, we have a small current of 0.18 amps. If we change the brightness, you see that our current drops and we have 0.03 amps. Now, during the short circuit test, you see that we have a current and a voltage, and in DC we know that power is the voltage times the current. However, this power is too small to be measured by this machine. Now we'll be looking at MPPT, which is maximum power point tracking, and as we change the irradiance, which is the brightness of the sun that is falling on the PV modules, we can see a change in the maximum power point at each percentage of irradiance. So right now we are at about 60%, and we're getting a DC voltage of 362 and a current of 2.35, which gives us a power of 850 watts. If we are at our maximum irradiance, we have a voltage of 357 DC and a current of 4 amps, and our power output is 1.4 kilowatts. Doing them in different configurations, we can get different outputs. Here we have our series configuration and our parallel configuration. So in a series array, we can maximize our voltage output of the panels as each voltage is added across the panel. So if we have 10 volts, 10 volts, 10 volts, we'll have a maximum of 30 volts across all 3 panels. Here, on the other hand, instead of the voltage being added, we are adding the current. So if we have 1 amp output of each, we'll have 3 amps out in total. In most cases, we have a combination of the two, where we get a desired voltage output. Let's say if each panel is 12 volts and we want 24 volts, we'll have 2 in series, and then we need a certain current, right? So we'll get 1 amp coming out of each panel, and we need 3 amps, we'll have 3 in parallel, and then coming across we'll have 2 by 3 to get the certain amount of power that is required for the load. So an inverter converts our DC voltage, which is a direct current, it's just straight and it's above the 0 volts line. Now with AC voltage, it's a sinusoidal wave which goes up and down. To get that sinusoidal wave, we use an inverter which chops the DC to get a staggering AC wave, and then we use various power electronics and embedded systems to get a pure AC wave. If we look here on the screen, we have around 50 hertz, and in Jamaica we use 50 hertz as our frequency, and this 50 hertz is in relation to the whole system that we have here for our solar plant simulation.